We're going to study our hypotheses tests in a similar way that we studied confidence intervals, in that we're going to look at how we apply a hypothesis test to proportions first, and then we'll apply it to means. And then in Chapter 10, we'll do the same thing again, except it's going to be two different populations that we'd be comparing, so it's a little bit different, but the overall concepts are the same. So here you have an example from your textbook where they're looking at contestants on American Idol, and they're wondering, does the person who gets to go last have an advantage? And there's, I think, a candy experiment that we looked at earlier in the year where they gave 5 different flavors of a candy, and they looked to see if when they said this is going to be their last one, if people tended to favor that one more than others. But at that point in the year, we were just looking at designing an experiment and not really thinking about how to see if the results are significant. Now we're in a place where we can determine if the results are significant. So if there are 12 different singers, then we would expect the person who goes last to only win a 12th of a proportion of times. So what happened in this particular study is they had 59 out of 600 contestants that went last, and they were preferred. So we want to see, is 59 out of 600 significantly greater than 1/12, the expected proportion if there's no difference. So your textbook authors do the same thing for a hypothesis test that they do for a confidence interval. They use their state, plan, do, conclude setup. It just looks a little bit different, right? In the statement, they state the parameter of interest, the true proportion of students who prefer the last singer, but now they also have to state a null and an alternate hypotheses. So again, the way I've set this up for this chapter is similar to what I do for confidence intervals, but I made a template. All right, and in your template, I just simply say, what's the parameter of interest? True proportion of students who prefer the last singer. You put in your null and your alternate. We have to give these conditions for inference. I noticed on your Chapter 8 test, a lot of you, when you got to, many of you just calculated the confidence interval. When it says compute and interpret a confidence interval, all of this should be part of it. And a lot of you just said this is the interval you calculated on your calculator, and you only get partial credit for that. Some of you, when you got to your conditions, you only listed like SRS, or you said they sampled less than a 12th of the population. We have to verify simple random sample. We have to sample less than a 10th of the population, and we also need a normal sampling distribution. So in this case, for proportions, it's n times p, n times 1 minus p. We calculate a test statistic. In this case, it'll be a z statistic and a p-value, and then we write a conclusion. So your textbook authors do the exact same thing, right? Here's their conditions for inference. Did we take a simple random sample? Did we take 10% of the population? And then do we have n times p and n times 1 minus p both greater than or equal to 10? And we show that that's satisfied. How do we get the test statistic? All right, we take the statistic minus the parameter and divide by standard deviation. So just like with confidence intervals, remember we use the z distribution for confidence intervals. We use it for proportions as well. We find a z test statistic. When we study means, this will be a t-value. All right, where's this formula coming from? If you look at your formula sheet and scroll down, not too far, you'll see it right here. It's the statistic minus the parameter divided by standard error. And the standard error has not changed, right? For proportions, it's still this same value. So you see that fleshed out here. The statistic was 0.098. Where did that come from? 59 divided by 600 is 0.098. That's where they're getting that. 59 divided by 600, they get 0.098. 0.083, what's that? That's 1/12, right? 1 divided by 12 is 0.083, and then we divide by standard deviation using p hat in there. P hat times 1 minus p hat over n. And they get a statistic of 1.33. So what we're trying to think about here is 1.33 statistically significant for an alpha value of 5%. Well, they find that the p-value is 0.0918. So again, remember what this means. They're saying ahead of time that we will make a type 1 error 5% of the time. We'll reject H0 5% of the time incorrectly when it's actually true. Okay, so they get a test statistic of 1.33, and they're saying the p-value for 1.33 is 0.0918. So that means there's more area in that tail, so I'll try to exaggerate a little bit, but our test statistic comes in here because there's 0.09 in that tail, so there's like an extra 4%. So we would say it's not significant, and we fail to reject the null hypothesis. On your calculator, what does this look like? We go to Stat, Test, and it's number 5, the 1 proportion z-test. So if you're keeping track here, we have a 1 proportion z interval from Chapter 8, a t interval from Chapter 8. In Chapter 9, we're going to have a 1 proportion z-test, and then a t-test. So here we have 1 divided by 12. And then what they found in their sample was that 59 out of 600 preferred the last one they saw. But our alternate hypothesis now is right-tailed. We want to see if this is significantly bigger than 1/12. Are they favoring that last person? And that comes from reading the context. So you calculate, and sure enough, here's your, so don't confuse these two. This is the new version of the calculator tells you this is p hat, this is the p-value. They're actually kind of close in value there, which would confuse some people. But this is your sample statistic. That's the 59 out of 600, 0.098. Just so happens that the area under the curve, the probability of getting this p hat or one further from 0.08 is about 9% as well. Okay, so if this p-value is bigger than alpha, which in this case is 0.05, we fail to reject the null hypothesis. And you can see the last line here, we want to keep it in context. There is not convincing evidence that there is advantage to performing last. There appears to be an advantage, but it's not statistically significant. All right, so in this next example, I want to kind of team these two together. I want to look at a hypothesis test, and then I'm going to look at the confidence interval that accompanies it. So I'm not going to redo like things that are on this template here for a hypothesis test, like parameter of interest and conditions for inference. I'm not going to restate those. Okay, I'm going to do them one time for my hypothesis test, but then when I do the confidence interval, I'll basically just compute the confidence interval because everything else will be done, and then we'll interpret it and see how the two things mean the same thing. Now, we need to wrap our heads around a little bit of context. Okay. In the financial world, there's a law, Benford's law states that the distribution of first digits is not the same. And I've talked about this before in class. If you ask a human to generate random numbers, usually there's a pattern, and they try to evenly distribute the numbers. Well, what Benford's law states is that, in fact, the first digit begins with a 1, not 10% of the time, as you or I might make it, but 30.1% of the time. It occurs much more often. So when people, like if an accountant or the IRS is looking for fraud, this is one of the ways they do it. They collect financial forms, they look at the digits, and if they notice that the digits are not following along with Benford's law, it's very possible that there could be some fraud, that they could be making these numbers up in their financial records and their expenses, and then they would look to further investigate to see if they can find the source of fraud. Or so we want to see if these proportion 68 out of 300 expenses is significantly different from 30.1%. And again, should AJL Associates do a more thorough investigation, this looks like justify your answer. A lot of times I'll have students just kind of give their opinion here. We don't want to do that. I'm going to justify my answer with a full tilt hypothesis test or significance test, so I have to use my my hypothesis test template. That's how I'm going to go about working through this. I'm going to use the template to do it. Okay. So first thing I do is identify my parameter of interest, which in this case is P. It's the true proportion of first digits that begin with the number 1 in this company's financial records. Okay, so it's the true, in this case, it's the true proportion of first digits that are 1, the number 1 in this company's record. So again, you can see one of the challenges inherently in applying statistics is being able to wrap our head around context. Like I have to read this long paragraph and figure out what the context is and how to articulate it in my language of statistics. So now we go to our null and our alternate hypothesis, and I've tried to make the null very easy for you by saying this should always just be a number. And again, we have to be able to read and comprehend the context here of what that P ought to be. It tells us that Benford's law states that it should be 0.301. That's where that's coming from, not making that up. So the challenge here is to make sure that you read very carefully through the context and then apply what we know about inferential statistics. Now the alternate, this is always a struggle. So far we've had a left-tailed test for the free throw shooter, and we had a right-tailed test for the American Idol example. Well, here in this case, it doesn't matter if the proportion is bigger than 30% or less than 30%. This is what we would consider a two-tailed test. So it only matters if it's different from 0.301. Okay, so for conditions for inference, we know that we need to have an SRS. Okay, we need to assume that we sample less than 1/10 of the population. So I need to list these, but I need to verify them. So this means that I assume they have more than 3,000 financial records. And for normality, they took a sample of 300. So we would say 300 times 0.301 is definitely going to be greater than 10. And then 300 times 1 minus 0.301 will also be greater than or equal to 10. Okay, both of those are true. Now for the SRS, we need to read and see. It says that they took a random sample of the records. So I'm going to state that. Okay, we put that in quotes. It says in the narrative that they took a random sample, so I write that down. Now I prefer to write the formula in symbols because I can get it right off the formula sheet. It's the statistic minus the parameter, like I showed you before. Right, just read it right off the formula sheet. Statistic minus parameter, right here, divided by standard error. And we can, again, look on the formula sheet to figure out what those are. But we should know when we're examining proportions that our statistic is p hat. Our parameter is p. So p hat minus p divided by standard error, which is p hat times 1 minus p hat all over n. So you want to at least write that formula. And then I would just let the calculator do the heavy lifting from here. I'm going to say I have a 1 proportion z-test. So if an AP reader is trying to read your work, you can lean on the calculator, but then just put the formula over here. Make sure you put the formula there to get full credit, especially if something goes wrong. Like if you give me the wrong z-value or wrong p-value, if you do this wrong, and I see your formula, I can maybe still come back and give you some partial credit. So let's see what happens here. We have stat test. It's the 1 proportion z-test again. We're testing this against 0.301, and we had, I messed this number up here, 68 out of 300. Make sure I get that number right. So I had 68 out of 300, and this is a two-tailed test. Right? So now we've seen all types of tests. We saw a left-tailed, right-tailed, and now a two-tailed test. Okay, so I get negative 2.81 for z. And then I get a p-value, and this is going to be important here. This is a slight difference from what we've seen before with the p-value, 0.005. Okay, so what you need to understand about this p-value is since it's a two-tailed test, it's the area in both tails. Okay, so what happens in this case is we don't care if we get a statistic to the left or to the right. It just has to be different from. So when we get this negative 2.81, and then we also have to consider 2.81. The p-value, 0.005, is the area in both tails combined. So if I only found the area in one tail, so if we change this to a one-tailed test, our p-value would get cut in half. I want to point that out to you. It's a very important distinction. So if we did this as a left-tailed test, right, and we just need to find something less than a critical value, this p-value will be cut in half. So really, each of those tails probably has 0.0025 in it. Okay, that's an important distinction on that p-value. But since it's a two-tailed test, it's the area in both tails. Right? So since alpha is 0.05, they never really stated it for us, so I would just use the same alpha all the time. We'll say for alpha is 0.05, we would reject H0. Okay, so what does that mean in context, though? If you go to the accounting firm and say we reject H0, that's not going to have a lot of meaning for them. What this means is that there is significant evidence that these financial records differ from Benford's law, so they should investigate them further. So we always want to make sure our conclusion is in context. Just like when we did a confidence interval, we'd say we're 95% or 99% confident of such and such. Okay. So let's look at the second part to this example then, where we look at the confidence interval and see if we draw the same conclusion. So remember, for part A, usually I would follow my confidence interval template. I'm going to skip that because the majority of the template stating the parameter, verifying the conditions is the same. Okay, I'm just going to go ahead and get the confidence interval, right? It's going to be p hat plus or minus z star, okay, times p hat times 1 minus p hat all over n. And we take the square root of that, okay? So when I calculate this confidence interval, I'm going to look to see if, since we did for alpha 5% significance test, a 95% confidence interval has the same meaning as a two-tailed test. Right? Remember, 95% confidence in the interval means there's 2.5% in each tail, which is exactly what's happening with a significance test. So this is a 1 proportion z test. We're going to go to stat, test, and this is a 1 proportion z test. Or I'm sorry, we're going to do the 1 proportion z interval this time, right? So stat, test, and we go to 1 proportion z interval. So same statistics, but we're going to tell the calculator to give us a 95% interval. Okay, so my interval goes from 0.179 up to 0.274. Okay, and I think I need to make a correction here on, I'm just not remembering what was on my template, and I don't have it anymore. But when we do normality for a hypothesis test, and even for the standard deviation, we use p and 1 minus p. So in other words, for this, the test statistic, just to differentiate between these two, the test statistic is p hat, statistics minus parameter. But down here, we don't have to use p hat. I can't remember what I put on that whiteboard there. I'll find out when I go back to put the questions in. I use p, all right? So this is for a significance test. All right, and then differentiate when we do a confidence interval. Because, and the reason we can do that is there's a claimed value of p, right? In H0, we say p equals such and such. In a confidence interval, we don't have that. So the confidence interval is just p hat plus or minus z star, and then we have to use p hat again. Okay, all over n. So very minor difference, but and I mean the only way it would make a difference is if you were plugging in, but you're going to use the calculator really to do all the work for you. So in part B, if we conclude that we are 95% confident, we're going to draw the same conclusion, but I feel like this is a little bit harder for us. What we should notice is that 0.301 is not a plausible value according to our interval. Okay, according to this interval. So indeed, we do arrive at the same conclusion. If we're 95% confident that p is in this interval, and the whole interval lives below 0.301, then that means we are 95% confident it's not 0.301. Doesn't mean we proved it, just means we have 95% confidence contrary to it. So the intelligent decision we would make based on the data is the same thing we did with the hypothesis test. We would believe that p equals 0.301 is not true. It's what we're believing to be true. It's an inference. It's not a mathematical fact. Okay, we haven't proven anything, but this is the decision we would make. We would suggest to AGL they probably should investigate further, run a more thorough audit. Okay, now this example takes us into considering what we mean by type 1 and type 2 errors and the power of a test. So I'm going to go through piece by piece. These two Polish math professors are spinning a coin 250 times, and they want to see if it's a fair coin. If it's a fair coin, in the long run, it should land on heads 0.5 proportion of times, half the time, which would be 125 out of 250. Well, they get a p hat of 140 out of 250, right? So the null and alternate hypothesis would simply be that P equals 0.5. That means it's minted properly, right? The alternate, however, they're not saying, nobody's suggesting that it occurs more or less than 0.5. Obviously, in our sample, it occurred more than 0.5, but we don't use our sample to create our null and alternate hypothesis. We just use the context, okay? So we have our null and our alternate hypothesis. Okay, so part B says, assuming the conditions for inference are met, that's good. That takes a little bit of work off of our plate. What p hat would lead us to reject h naught at a 5% significance level? So remember, this is a two-tailed test. So there's actually two p hats that would lead us to reject it, and they should be familiar to us. We know them, all right? We have a p hat that lives here, or I guess it wouldn't be p hat, it would be the z star, okay? And then there's a p hat out here. If this is 5% significance, and that means there's 0.025 in this tail and 0.025 in this tail. So we would arrive at this with inverse norm. Okay? If it's fair, we believe 0.5 lives in the middle. So if we get a z star, or in this case we're going to want to get a p hat that lives above here to the right or below to the left. So what would those sample proportions be? So I want to inverse norm. I want to find an area to the left of 0.025, okay, or 0.975. There's two of them, right? And in fact, the one that we got looks like it's going to be higher, right? So the mean of this sampling distribution is 0.5, and then what's the standard deviation? Well, we've done this before. The standard deviation for these p hats is going to be p times 1 minus p divided by n, which was 250. And then we'll take the square root of that. So either one of these p hats here would give us convincing evidence that the coin was not minted properly. One too far below 0.5 and the other too far above 0.5. And these are the two p hats I get, 0.438, which obviously we didn't get one that was below it, or 0.562. Okay? So what p hat did we get? We got 140 out of 250, right? And that's 0.56. So without actually running the test, we would conclude that we would not reject the null hypothesis. So part C says, based on your answer or to part B and the results of the study, what conclusion would you draw? We would have to conclude that we don't have significant evidence that it's minted improperly. Now we came awfully close though. If you want to check it on the calculator, what would we do? We would do stat test, and this would be a 1 proportion z test. We're going to test 0.5 against the 140 out of the 250 that we got, and it's a two-tailed test. So we're going to expect our p-value is going to be a little bit bigger than 0.05, and it is. It's 0.058, okay? So if we take the direct hypothesis test approach and look at the p-value compared to alpha, the p-value is bigger than alpha, so we would fail to reject h naught and not have significant evidence there. This question in part D is not really something we need to spend a lot of time on, but it will help us understand the idea of the type 2 error and the power of the test. You're always going to see something like this when we start thinking about the probability, and this is not on the AP exam where you have to actually calculate this probability, but they're saying, suppose we know that this is actually 0.55, okay? So the correct decision is going to be to reject the null hypothesis. Our null hypothesis was that it was 0.5. What's the probability that we don't reject it, okay, when it's actually false? Right? That's what the probability of the type 2 error is. And we saw earlier that I created these critical values, and we saw that the only way we were going to reject the null hypothesis, we were only going to reject it if something fell outside of this. So we're rejecting the null hypothesis if we get something in this area or we get something in this area. Now, it's going to be really unlikely we get something in that bottom green area, but So our null hypothesis is kind of wrong. Our null hypothesis is that it equals 0.5 when it actually equals 0.55. So the correct decision is going to be reject the null. It's like we have a guilty defendant. So the correct decision is to find them guilty and reject their claim of innocence. Well, we're only going to do that in this green area, right? So the probability that a type 2 error will be committed is my red area down here. So how do I get that? Normal CDF, lower critical value to the upper critical value. I'm only going to the green areas that I've shaded is correct decision making, okay? But we don't know that. We never are able to peek behind the curtain. Mean is 0.55, and then our standard deviation is 0.55 times 0.45, right? 1 minus 0.55 over 250, and we take the square root of that. Okay, so 0.648 is our probability of the type 2 error. The power of the test, which is what they ask us for in part E, would be 1 minus that, right? The probability that we find convincing evidence, if that's true, would just be 1 minus 0.648. So what I want to really clarify here is parts D and E of this question. Would this be something that we would ask on an AP exam or make a big priority? No. What you certainly do need to know is that the type 1 and type 2 errors battle against each other, right? If alpha is 0.05, then you're more likely to reject a null hypothesis than if alpha is 0.01. Generally, we don't want to change the significance level around, right? That's going to be non-negotiable from the start. If you're more likely to reject the null hypothesis, then you're less likely to fail to reject it, right? So if you're less likely to make a type 1 error, then you're more likely to make the type 2 error, right? If you're more likely to reject a null, then you're less likely to fail to reject it, and vice versa. They kind of go against each other. Ultimately, we want to try to make that correct decision. The way that we could feed, again, it's not advisable to change the alpha level, but you could. If you change alpha from 0.01 to 0.05, then you'll be less likely to make a type 2 error, but you'll be more likely to make a type 1. Generally, you don't want to play around with that. The way to feed both animals would just be to get a bigger sample size. If I get a bigger sample size, then my p-hats will generally be more precise and closer to the true value of p. And then in that case, I'm less likely to make either error.